Here we go.
Thank you. Good morning, everyone. We're doing the case studies now. And last class I did 4 on aluminum and silica type refractories, and I'm going to try to do 4 for each remaining class. So I have 4 more today on aluminum and silica, and I sent the first 8 papers to Greg at the American Ceramic Society. So hopefully he was able to forward you the PDFs of these. And so we'll have 4 on aluminum silica today, and then Thursday we'll do 4 on basic refractories. So the first one here, fracture energy and thermal stress resistance parameter of a high aluminum brick. This is a 1986 paper, and they looked at this parameter, RST, the thermal stress crack stability parameter, and they calculated this as a function of temperature from room temperature to 800 C. And then they try to correlate the RST values with the thermal shock resistance, which was done by rapid quenching, water cooling quench, so very severe conditions. So this kind of makes sense. Measuring properties as a function of temperature. Most people measure strength and modulus and calculate the R parameters at room temperature. But when you're thermally shocking a material, it's at a high temperature, and these properties are different at the high temperature. So if you're going to be very thorough, you really want to measure all these properties: strength, modulus, thermal expansion, work or fracture, as a function of temperature, and calculate the R parameters, because they will change. So these people did this as a function of temperature. So they had a 70% alumina D70 and an 80% alumina K80. So the alumina content here was 70 and 78 weight percent. Bulk density goes up slightly with higher alumina content, from about 2.81 to 2.98. Porosities are quite similar, 14, maybe 13. The strength goes up with the alumina content. This is a compressive strength in megapascals, 92 and 156. And the coefficient of thermal expansion on these are pretty low, 6.3 times 10 to the minus 6 per degree C. So the 80% alumina is basically a stronger, slightly lower porosity material. So the D70, 70% alumina brick was made with andalusite and sillimanite. The K80, the 80% alumina, was a synthetic aluminum material. So the mechanical properties, again, were measured from room temperature, 800 degrees C. They measured Young's modulus by a dynamic technique, 3-point bend strength, and a fracture surface energy with the chevron notched bend bar. So the thermal shock samples were 2.5 by 2.5 by 15.5 centimeter bars. That's pretty much the normal quenching size type bar. The quenching was from 800 degrees C to room temperature water. And one cycle, so just one quench cycle, and then they measured 3-point bending and the bending strength to monitor the damage. So this was the configuration for the chevron notch. H, the distance from the top surface to the point of this triangle. And D is the full thickness. So H over D was approximately a half. So this diagram is pretty accurate. H is approximately half of D. So they used the chevron notch sample. So this is for the 70% alumina and then the 80% alumina. The test temperatures were 25, 200, 400, 600, 800. Same for both materials. And then they measured the MOR, or the bending strength, in megapascals. So this goes from about 12 to 17. There's an increase because of stress relief at the higher temperatures. And this one drops slightly with temperature. There's no stress relief here. Young's modulus goes from 20 to about 40 million, again, due to stress relief. And then this one goes from about 70 to 62, declines with increasing temperature. And that's times 10 to the 3 megapascals. The K1C in megapascal square root of meters goes from about 1 to 1.3 for the 70%, and then maybe 1.9 down to 1.7 for the 80% alumina. The work of fracture in joules per square meters starts at about 67, goes up to about 113. So this increases with temperature. This one starts to decrease slightly and then increase. So there's some plastic deformation here giving rise to the higher work of fracture values at 800 degrees C. Poisson's ratio 0.2 and 0.18. And then they calculated RST, square root of meters, degrees C. These values are all around 8 for the 70% alumina and around 4, 4.5, 5 for the 80% alumina. So the 70% alumina should have the higher thermal shock resistance. The retained strength, these barely lost any strength. They're 11 down to maybe 10. And these lost about half their strength after thermal quenching, 26 to 13. They're still stronger than the 70% alumina. So the 80% alumina is still stronger, but it did lose half its strength. So if you plot hot MOR versus temperature, this is D70. There's this increase because there's stress relief, most likely a plastic or glassy phase forming. And then the K80, 80% alumina has a gradual strength loss. Young's modulus, the 80% alumina has a gradual loss in Young's modulus. And then the 70% has a gradual increase, again, due to a stress relief. This is in megapascals times 10 cubed. So these are 20,000 to 80,000 megapascals. Then the work of fracture in joules per meter squared versus temperature. The 80% alumina is lower than the 70% alumina. So the 70% alumina has more resistance to crack propagation. And they're both starting to increase at the highest temperature, and that's due to some type of plastic deformation process. So when they looked at the fracture surfaces, the 70% alumina had transgranular fracture. So the coarser grains were fractured through the grains, and the fracture went also through the needle-like matrix, which was the mullite in the matrix. So this was a pretty coarse microstructure with transgranular fracture and fracture of the needle-like crystals of the mullite in the matrix. The 80% alumina had a much finer microstructure, and now the fracture, instead of being through the coarse grains, was intergranular. So it went around the finer grains. And you don't see the needle-like mullite structure either. So in the lower alumina content, the 70% alumina, the microstructure was coarse with large grains. These were andalusite or sillimanite coarser grains, and they were substantially microcracked. So you can see the microcracks in the coarser grains substantial microcracking. And when the fracture took place through the coarser grains, this transgranular fracture, it was a step-like fracture pattern. So this is a higher magnification of a fracture through a coarse grain. And you can see it sort of following cleavage plane. So it is not a flat fracture when it's going through the coarser grains. It is this step-like pattern. So that appears, that pattern appears to absorb more energy and is somewhat responsible for the higher work of fracture. The larger grains in the 80% alumina, you can see the pore structure, the dark circles are the pores. They were not microcracked, so they were pretty much microcrack free. So fracture toughness, megapascal square root of meter versus temperature, and K1C is the resistance to crack propagation also. 80% alumina had a higher toughness compared to the 70% alumina. And they both, at the higher temperature, start to increase because, again, it's plastic deformation at the crack tip. And if you looked at the retained strength in megapascals versus the temperature, you can see the 80% alumina had a drastic strength loss starting at delta T's around 400. And D70 was pretty constant. So the 70% alumina had much lower strength loss. It started out at lower strengths, and that's how a lot of refractories are designed to have low initial strength, but very little strength loss as a function of quenching. So when you look at it in terms of retained strength, the 70% alumina has better thermal shock resistance. And so the percent retained strength versus temperature, this is 100%. So it looks like D70 lost about 10% of its strength, and then the K80 lost about 50% of its strength. So based on retained strength, you would say that the 70% alumina fared better during the quench test. And if you calculate RST, the square root of meters degree C, and so D70 is roughly 8 to 9, and then K80 is about 4.5, 5. So based on RST calculations, the 70% alumina should have better thermal shock resistance. So this table summarizes the results, the test temperatures from 25 to 800 degrees C, calculated RSTs. These are being around 8 or 9 for the 70% alumina, and the 80% alumina around 4.5 or 5. And the much better retained strength for the 70% alumina. Actually, it has 84% of its retained strength at 800 degrees C quenching. And then the 80% alumina only has 50% of its strength. So for the summary here, they're saying the coarse grains that were microcracked with this transgranular step-like fracture required more energy for fracture than the microcrack-free finer grains of the 80% alumina material, which mostly had intergranular fracture. And they're also saying the needle-like mullite matrix also required more energy for fracture. The RST value is correlated with the thermal shock resistance by rapid quenching, which is a water-cooled quench. And they're saying RST values calculated at room temperature may not be as reliable compared to values calculated at elevated temperatures, as these calculations are somewhat temperature dependent. And especially if the deformation is beyond the elastic range. So these are only measured from room temperature to 800 degrees C. So they're not really extremely high temperatures where you would expect the mechanical properties to change much more rapidly than from room temperature to 800. So they're basically pointing out the importance of, if you're going to calculate R4 prime or RST, and you're going to quench from high temperatures, it's probably more relevant to make these measurements at high temperatures. Actually, I would, if I were modifying microstructures for thermal shock resistance, I would measure the appropriate properties such as modulus, strength, worker factor over the entire temperature range. The next paper is the effect of mullite on mechanical properties and thermal shock behavior of an aluminum mullite refractory. This is a 2003 paper. So strength, Young's modulus, fracture toughness were measured on aluminum mullite refractories with and without the addition of needle-like mullite particles. So one of the materials had a matrix with a great deal of needle-like mullite particles. So the resistance to fracture initiation and fracture propagation were correlated to thermal shock resistance. So they calculated R and RST. So there were two aluminum mullite type bricks. They had a constant mullite to alumina ratio. Brick A had coarse and medium alumina mullite particles and a fine matrix of mullite needle-like crystals. These fine mullite particles were in the order of 5 microns. And then brick B, coarse and medium alumina mullite particles. So no fine mullite particles added to this one. These were slip cast and sintered at about 1600 degrees C. So these mechanical properties were measured at room temperature, fracture strength by 3-point bending, a static Young's modulus. So this was measured from the 3-point bending strength, stress strain curves or load displacement curves. So they're just taking the static modulus, which is just as the slope of a stress strain curve. And fracture toughness was measured by a single edge notch beam bend bar. The thermal shock samples were 15 by 1 by 1.5 centimeter bars, and their water quenched 5 bars from these temperatures, 1200, 900, 600, and 300 down to room temperature. So one cycle per bar for the water quenching, and then they measured the 3-point bend strength to monitor the damage. So the strength in megapascals for A was about 10, B was around 8. The modulus in gigapascals was about 9 for A and about 7 for B. K1C, again, typically in megapascals, square root of meters, 0.7 and 0.5. And then gamma F, and that was calculated off of the fracture toughness. So that's a fracture initiation. And joules per meter squared, 25 and 18. So the fracture surface energy was for crack initiation. C is the crack length. In these materials, 1.2 and 1 millimeter. R was calculated and degrees K, 115 and 99. So you have to add 273 degrees to this to get degree C. Then RST was calculated in square root of meters, square root of temperature, 1.1 and 0.8. So not really great differences. So all of these materials were approximately 90% alumina, 10% silica. So the silica reacted with the alumina to form mullite. So this is sample A. This is a 200 micron bar. So these are our coarse aluminum mullite grains. in a finer mullite type matrix. So there's a crack in this grain here. So there's a crack in an aluminum mullite grain, and that's due to tensile stresses from the thermal expansion mismatch when the material is cooled. So mullite has a pretty low thermal expansion, 4.5 times 10 to the minus 6. And then alumina has a much higher thermal expansion, about twice mullite, 8.6 times 10 to the minus 6. So the alumina upon cooling is shrinking a lot more than the matrix, so it puts it in tension and these cracks result. The crack grows and then it's arrested in the mullite matrix right there. So the EDS type analysis, this is for alumina, this is for silica. So you can see the higher alumina content in the alumina-rich coarse grain, and then the higher silica content in the matrix where you have the mullite present. So still sample A, this is now 20 micron bar, so it's much higher magnification. And they're just showing the alumina here, and then silica. So this is the mullite matrix, and it's hard to see, but there are cracks that are arrested in the mullite matrix due to crack deflection and branching mechanisms. So when the crack hits the mullite needle-like matrix, there's crack deflection and crack branching to arrest the crack. So if you plot strength versus delta T, the diamonds, the dark diamonds are A, the open circles are B. So the strength is a little bit better in sample A. This is the one with the mullite matrix. So the thermal shock resistance is a little bit better in A than B. The modulus follows the same trend, a little bit higher modulus in A versus B. So again, A has the mullite matrix, and the thermal shock resistance of A was greater than B. So the sample A has both intergranular and transgranular fracture. This is for the 1200 degree C quench. So this is pretty high magnification in the matrix. So you can see here, this particular crystal is transgranular fracture, and then these other crystals, the fracture goes around the particles. So that's intergranular fracture. And sample B is mainly intergranular fracture, and this is again for a 1200 degree C quench. Here's a little bit of transgranular fracture over here and maybe over here, but mostly intergranular fracture. So for these two samples, for the microstructure, when you add needle-like mullite particles, they're claiming improved resistance to thermal shock by pull out and crack deflection mechanisms. So the matrix is micro-cracking. They're claiming a weaker interface between the mullite matrix and the aluminum mullite particles. That activates some of these crack deflection mechanisms in the matrix. So improvements in strength, Young's modulus, and fracture toughness by adding the needle-like mullite particles. And when you calculate R and RST, so the resistance to fracture initiation and fracture propagation, correlated with improved thermal shock resistance. So these weren't major improvements in thermal shock resistance, but definitely a mullite type matrix in an alumina silica type refractory certainly makes an improvement in thermal shock resistance because it can activate toughening mechanisms with that needle-like structure. This other next paper is thermal shock behavior of a kaolinite refractory. So this is kaolinite clay. So it's more of a fire clay material. And they're measuring the thermal shock behavior as a function of the organic binder content. So the organic binder content affects how the material is densified during the forming operation. So they measured R prime. So R is for crack initiation, rapid quenching. R prime is for more gradual quenching because it has the thermal conductivity component in it. And what's called R3 prime. And we didn't discuss R3 prime, but here's R4 prime, which we discussed. Is the fracture surface energy from the work of fracture times the modulus divided by the fracture strength squared and 1 minus 2 Poisson's ratio. R3 prime is exactly the same, but it doesn't have the fracture surface energy term in it. So R prime and R3 prime were correlated to the thermal shock damage for this clay-based refractory as a function of the binder content. And these organic binders have been shown to increase strength, increase thermal conductivity because they increase the density and decrease the porosity. So I don't particularly like using R3 prime because in my opinion, it ignores the most important mechanical property that you can measure for thermal shock, the work of fracture. If I were measuring just one mechanical property and trying to alter microstructures to improve thermal shock resistance, I would measure gamma F. In this case, it's the work of fracture. So you can use R3 prime to compare materials with similar crack propagation mechanisms and still rank the materials, but the crack propagation has to be similar. So they use a kaolin clay and an organic binder, and the binder concentrations were varied by diluting a fixed volume of an undiluted binder with different volumes of water. So they were just diluting the binder and diluting the viscosity. So the binder concentrations were normal with the viscosity of the undiluted binder. And they made samples in two different ways, a 1.5 centimeter diameter by 15 centimeter long round bar that was extruded, and a 4 centimeter diameter by a 4 centimeter thick cylinder was pressed, and they were fired at only 1150 degrees C, which is probably the appropriate temperature range for a clay. So they measured mechanical properties at room temperature, a bend strength and 3-point bending on the rods, the 1.5 centimeter diameter by 15 centimeter long bars. They measured a dynamic Young's modulus by using an ultrasonic velocity technique on these shorter cylinders, the 4 centimeter diameter by 4 centimeter long cylinders. The thermal shock was done on the longer cylinders, the 1.5 centimeter diameter by 15 centimeter long bars. It was done with water quenching, and they averaged 10 bars per quench temperature. And these were the quench temperatures: 600, 500, 400, 345, 300, 270, 200, and 100. And the water was at 20 degrees C, only one cycle per quench. And they monitored the damage with a 3-point bend bar. And the damage parameter, DMOR, just equals 1 minus sigma delta T divided by sigma 0. So sigma 0 is the strength of the fire samples that were not thermally shocked. So that's the initial strength. And then sigma delta T was the strength of the samples after they were thermally shocked at one of these delta T's. So if there was no change in strength at a particular delta T, this term would be close to 0, and the damage parameter would be close to 1. If there was a lot of damage, say at a higher temperature like 600, this would decrease, and this would be some number much less than 1. So as D decreases, the damage increases. So they plotted bulk density as a function of binder concentration. So it was normalized, so it goes from 0 to 1. So the square here is with no binder. It's just using water mixed with the clay. And then the X's are the samples that were plasticized with different binder contents. So you can see the density increases with increasing binder content. It's a maximum about 0.7. Then it starts to decrease because now you have too much binder present. So the optimum binder content is about roughly 0.7. This is a partial composition of the binder. You can see there are different metal oxides present, like MgO, alumina, iron oxide, silica, potassium, and sodium oxides, and lime. The important thing is there's about 1.5% ash content from these metal oxides. So these oxides in this ash are really fluxes. So they're impurities, and they flux the system. So we plot, or in this table, it's listed the normal binder concentration normalized from 0 to 1. So the control sample has no organic binder. So it's normalized from 0 to 1. The porosity basically decreases with binder concentration. The thermal conductivity at room temperature in watts per meter degree C increases up to about this 0.7 optimum binder content. And then you can see the porosity is starting to go up a little bit. The conductivity is going down. And the modulus in GPA and MR and MPA, they're following the same trend. So the modulus goes up to about the optimum binder content and then starts to decrease. So this is about 33 GPA. And then MR increases and then starts to decrease. So this is 106 megapascals. So R for fracture initiation, rapid quench conditions was calculated in degrees C. And it reaches a maximum in this same region. R prime for a more gradual quench. Again, it reaches, and this is in watts per meter, a maximum in this about 0.7 binder range. Then R 3 prime times 10 to the minus 6 in inverse pascals starts out high at 16 and then continues to drop around 3 or 4. I'm not sure why they're much interested in R and R prime, because these are going to be low numbers for a refractory material. They're always going to be low because of the microstructures of refractories. So the damage parameter DMOR from 0 to 0.8 as a function of the quenching temperature. And then these are the different samples. The X is the material without the binder. So the damage goes up slightly, and then a critical value somewhere greater than 325 degrees C for the delta T, there's an abrupt strength loss. So these are for all the materials with the organic binder. They have the greatest damage compared to the sample without a binder. So this is the optimum binder concentration, about 0.68. The delta T is 180 degrees C. So when they looked at this microstructure, they said that, well, there's no microstructural features in this fracture surface that look like there's significant strength degradation. And this was with no binder. Again, the delta T was 180. So these are pretty low delta Ts. And again, they saw no significant damage to this microstructure. But then when you go to the higher delta T, this is 580 degrees C at the optimum binder content of about 0.68. Now they start to see large matrix micro cracks. So here's a coarse grain. So there's micro cracks between the coarser grains and the matrix following that path. So they're seeing large cracks develop with where the binder concentration was the optimum at this quench temperature, 580 degrees. And then this is for no binder content at the higher temperature, 580 degrees C. And they're seeing few characteristics of strength degradation like severe microcracking. So the normalized thermal shock parameters are R prime and R is R3 prime. Look like this. So the dark circle is R, the open circle is R prime. So the R parameters as a function of binder concentration, and then the triangles are R3 prime. So these values go up somewhat. So there's more damage as you increase the binder content. And then the, well, I'm sorry, these are just the thermal shock parameters. So R prime increase somewhat with increasing binder concentration, but R3 prime drops off drastically. So the material without any binder has the best R3 prime. So refractories with higher binder contents showed severe matrix cracking. So these were the denser materials, the lower porosity materials, compared to the refractory with no binder content. So when they looked at the thermal shock parameters R prime, and R3 prime, they correlated the thermal shock damage as a function of binder content. So R and R prime increase with increasing binder content. Basically, they're saying, well, that increased the resistance to a crack initiation. And then R3 prime decreased with increasing binder content. So as the binder content went up, it was harder to start a crack initiation, but it was easier to propagate a crack. So without a binder, it had the highest resistance to crack propagation and the lowest resistance to crack initiation. And that's pretty typical of a material that would have better thermal shock resistance. So high binder content at higher strength before thermal shock, but lower retained strengths after thermal shock. And that critical delta T was about 325 degrees C. The sample without any binder had lower strength before thermal shock, but higher retained strength after thermal shock. And again, the critical delta T was in this 325 degrees C range. And then the fourth paper, mechanical properties of mullite corundum composites. And these were prepared from different bauxites. So they were looking at the effect of in situ mullite content on mechanical properties. So a bauxite will form mullite if you have silica present. So R and R3 prime were correlated to experimental thermal shock damage. So again, R4 prime has this work of fracture term in it. R3 prime does not. So R3 prime was used to compare materials with similar crack propagation mechanisms. I'm not sure how you prove they're similar, but it's kind of a shortcut in my opinion by not measuring the work of fracture. And again, if I were developing a refractory with an improved thermal shock microstructure, if I were to measure one property, it would be work of fracture, especially as a function of temperature. Uh, so these mullite corundum compositions were prepared from bauxite, plus they added colloidal silica to form the mullite. So the silica reacts with the bauxite in situ, forms a mullite. And the mullite contents were 70, 80, 90, and 100% mullite. 6 by 6 by 75 millimeter bars were isostatically pressed and sintered at 1600 degrees C. You can easily form mullite at 1600 degrees C. So M is 100% mullite. MC10 is 90% mullite and 10% corundum or alumina. MC20 is 80% mullite and 20% corundum. MC30 is 70% mullite. And BL is just bauxite. So that would be 100% corundum. The raw materials here, bauxite and silica, these are how they were mixed in terms of grams. So you can see the silica is highest where you have 100% mullite. So this is probably the right ratio to convert all the bauxite to mullite. And then the silica content decreases and the mullite content decreases. So 3-point bend strength, room temperature, 900, 1,000, 1,100, and 1,200 degrees C. So they measured strength as a function of temperature. And thermal shock was multiple air quenches from 1,200 degrees C to room temperature. So this is not as severe as a water quench. And these quench bars were done in cycles of 3, 6, 9, and 12. And they monitor the damage by a bend bar strength. So this is a X-ray diffraction pattern, intensity versus the angle 2 theta. M is mullite, C is corundum. So this goes from 70% mullite to 100%. It's not quantitative, it's just qualitative. But if you look at like C for corundum, the peaks get more intense as the corundum content goes up. So basically, they're just showing you have corundum and mullite present, just verifying they made mullite at that firing temperature. So they measured linear shrinkage versus the composition. So this is 100% mullite, and then this would be 100% corundum. So you can see the shrinkage goes up as the mullite concentration goes down. So maybe 22 to 30% shrinkage. So basically, they're saying there's more impurities present as the alumina content goes up, impurities from the bauxite. So that gives rise to the shrinkage behavior. So increasing shrinkage with increasing alumina content. So the same plot, linear shrinkage versus the mullite corundum compositions. And the numbers are now the bulk densities in grams per cubic centimeter. So the higher the shrinkage, the denser the material. This goes from about 2.5 to almost 3.5. So big difference in density. And then the porosity, there's a big difference in porosity. So it's the same plot, linear shrinkage versus the composition. So the mullite material had about 21% porosity, then the material that's all corundum, only 0.8. So it's very dense, low porosity. So if you look at flexural strength as a function of composition, and then flexural strength on the left-hand side, modulus is on the right. Strength is in MPa, modulus is in GPa. So the black curve is the strength, the red curve is the modulus. So these materials going from left to right are getting much more dense. So the strength is going up, the modulus is going up. This is where the porosity decreases. So they're saying, well, there's increased glass content responsible for the shrinkage and decrease in porosity, and that's giving a much higher strength value with increasing alumina content, and also a much higher Young's modulus. So the composition labeled M, which was all mullite, you can see the needle-like crystals of mullite. You can see the porosity, and then you see a lighter phase. That's probably an impurity silicate type phase. There's not a whole lot of it there. You see mostly the needle-like mullite crystals. These crystals are interwoven and interlocking. They make a pretty good material in terms of strength and give high fracture surface energies. MC20, 20% corundum. You can see there's the porosities there, it's even less. You can't really see the developed mullite structure, but you can see this a lighter phase. There's quite a bit of it. That's the impurity phase. That's probably responsible for the densification. And then the one that's all corundum. You see very little porosity in this one. You don't see the needle-like mullite crystals anymore because they're not there, but you also see this lighter phase in quite a few locations. That's the impurity phase. So the calculations for R and R4 prime, R in degree C, I'm sorry, R3 prime. I keep thinking always R4 prime because I don't know why anybody does R3 prime. But anyway, R3 prime is in megapascals. So M is 100% mullite, BL is 100% corundum. So R goes down as the material becomes denser, you would expect that. And then R3 prime also goes down, and you would expect that to decrease as the density goes up, and you're losing the mullite needle-like microstructure. So Hadamard versus temperature looks like this. This one in the star in black is the corundum, and it really falls off in strength as a function of temperature because of the impurity phases present. But the blue here, the diamond dots here, pretty steady. The mullite really doesn't lose its strength, and maybe there's a little stress relief here. And the other ones with 10, 20, 30% corundum are still pretty constant with temperature. They don't really fall off significantly. It looks like there's a little stress relief due to a plastic phase being formed, a glassy phase. So the percent change in hot MOR, and again, M is all mullite, BL is all corundum. And these are the testing temperatures, the quenching temperatures. So it's normalized to 100%. So you can see that the mullite material actually got a little bit stronger, probably because of the plastic phases doing responsible for stress relief. So these weren't really degraded during thermal shock. The MC10 and MC20 were also pretty good. they showed a little bit of strength increase. The MC30 started to fall off in strength, so 100% down to about 80%. And then the corundum really fell off in strength from 100 to about 34%. So flexural strength versus the number of quench cycles. This one, the black curve for the corundum, this actually is not on this plot. It should be up here around 200, close to 200. When it went more than 3 cycles, it really fell off in strength. And then the blue is the mullite. You can see that it was pretty constant as a function of the number of cycles. And then MC30 is somewhere in between mullite and corundum, this red curve here. And then the green and this other like burgundy or not too bad either. This one lost a little more strength, the one with the MC10. So the percent change in flexural strength as a function of thermal shock cycles. So the cold MOR, 3 cycles, 6 cycles, 9 cycles, and 12 cycles. This one just dropped slightly, maybe 5%. This one dropped about 14%, about 13%, about 30%, and about 48%. So decreasing mullite content, more damage during thermal shock. And they also plotted elastic modulus over the initial elastic modulus E0 as a function of the thermal shock cycles. And same trend as for strength, the black curve here with the stars was for corundum. So after 3 cycles, it fell off significantly. And then the blue curve, all mullite, had some damage, but it didn't have a significant drop in the modulus. And then the other mullite compositions, 10, 20, and 30 were in between these two. So they're saying refractories with the highest in situ mullite content showed the highest thermal shock resistance. And then the test methods R and R3 prime correctly predicted the thermal shock damage. I think that's the last slide for today. So we looked at quite a few aluminosilicate materials, and you can see that people look at all different ways of quenching the materials, all different temperatures, some severe quenches with water, some less severe air quenches, all different sample shapes and sizes, and they're calculating, or they're measuring a variety of properties and calculating different R parameters. But I think the best way, if you're looking at a microstructure variation to improve thermal shock, is to look at R, ST, and R4 prime and measure what we call gamma MBT and gamma WF, strength and modulus, all as a function of temperature. That's the most complete way of looking at this, and then correlating it with the thermal shock performance, and then looking at the microstructure, the fracture surfaces, and seeing what the fracture paths are. So that's the most thorough way of doing it. All of these papers are some variation of that. So have a good rest of your day. On Thursday, I'll do some studies on basic refractories, MgO, chrome, MgO, and then spinel, which is the magnesium alumina material replacing, that's pretty much been replacing the chrome magnesite materials because of the problems with chrome. So I'll do at least 4 of those on Thursday. Again, have a good rest of your day, and I'll see you in 2 days. Thanks.